Hello everybody. What we're going to be focusing on today is solving trigonometric equations, which is something you've done a little bit with whenever we were working with right triangle and non-right triangle trigonometry, but you've not done it with the unit circle before, and we're going to incorporate the unit circle with solving trigonometric equations. And specifically, you're going to use the unit circle to solve trigonometric equations for a specified domain, and you'll understand what that means shortly. Before we get into that though, there are some things that we've been focusing on in this chapter so far and in our previous chapter that you absolutely have to know in order to be successful with solving these trigonometric equations. So I want to briefly mention these. I'm not going into detail on any of it because there are other videos out there that talk about it. It's prior knowledge after all. You absolutely have to know the unit circle in the first quadrant. Really, you need to know it for the entire thing, but if you know the values within the first quadrant, then you can do okay, because whenever we're looking at values in the second quadrant or third quadrant or fourth quadrant, we can simply use reflections of these 5 points right here in order to find out what the values are in the other quadrants, right? Okay, so you need to know the cosine and the sine values for each of these 5 points right there. Alright, secondly, you're going to need to know the various positions on a unit circle at which two angles would have the same sine or cosine or tangent value. So you'll remember that two angles that are supplementary have the same sine value, which is what these equations say, one for degrees, one for radians. You'll remember that when the sum of two angles is 360 degrees, or 2 pi radians, as these equations would specify that they had the same cosine value. And you'll also recall that whenever two angles are 180 degrees or pi radians apart from one another, halfway around the circle from one another, that they're going to have the same tangent value. Alright, one more thing. You'll need to remember how to find coterminal angles. And a coterminal angle is simply an angle that is exactly 1 or 2 or 3 or 4 or so on revolutions around the circle from a given angle. Alright, so theta is coterminal with theta plus or minus k times 360 degrees. In other words, if I take an angle and add 360 degrees or 720 degrees or 1080 degrees, any multiple of 360, as long as that value k is an integer, that gets me an angle that's coterminal with where I started. And in radians, if you add 2 pi or any multiple of 2 pi with an angle theta, it gives you an angle that is coterminal with that original angle theta. Okay, so that's the prior knowledge. Let's get into solving some equations using the unit circle. Alright, and let me give you an idea of what you're going to have to think of whenever you're solving these equations. First of all, when I say you're solving a trigonometric equation, what I mean is you're solving an equation where the angle is the unknown value, and the angle is hidden within a sine or a cosine or a tangent. Alright, secondly, it turns out to be impossible just to solve, at least as far as the unit circle goes, an equation like this without a specified domain, at least not if you want a limited number of solutions. And I'll explain that as we go through this trig equation. Every trig equation that we're going to solve is going to have a specified range of values. Alright, it's going to have a specified domain that we're going to have to focus on in order to figure out what the solutions are that we're looking for. In this case, we're only looking for values of x that are between negative 360 degrees and 360 degrees. Alright, now I told you that you're going to have to know the unit circle in order to solve a trigonometric equation. This is about as simple as they get. I'm telling you that the cosine of some angle x is equal to 1/2. Well, so what we need to do is think about where on the unit circle is a point whose x coordinate, because we're dealing with cosine, would be 1/2. And it turns out that the first one, there happens to be one in the first quadrant, and that happens to be when the angle is 60 degrees. Okay, now another thing that I forgot to mention is that you see how the specified domain was given using degrees, which means we want our angle measures for our solutions to be in degrees. Had this range of values been in radians, we would have given our answer as pi over 3, not as 60 degrees. All right, so 60 degrees has a cosine that's equal to 1/2. We know that. But what we're trying to do is we're trying to find all the angles between negative 360 and positive 360 that make that true. All right, well, remember that if two angles add up to 360, that they have the same cosine value. So another value that we automatically know is going to have a cosine of 1/2 is going to be 360 minus 60, or 300 degrees down here. So we've got at least two solutions to this equation so far. I'll start writing out the solutions momentarily. But we've got to make sure we find all the angles between negative 360 and 360, right? What we've done is we've found all the positive angles between 0 degrees right here and positive 360 degrees that have a cosine that's equal to 1/2. But what we also need to do is think about what are the angles that are coterminal with each of these that are going to be between negative 360 and 0. Now remember, when you're finding coterminal angles with degrees, you would either take an angle and add 360, a multiple of 360 with it, or you would subtract a multiple of 360 from it. In this case, it wouldn't make sense to add 360 because then we'd have 420 degrees right here, and that's greater than our specified domain for this equation. But subtracting 360 makes plenty of sense. 60 minus 360 gives you negative 300. Negative 300 degrees is coterminal with 60 degrees, and it's between negative 360 and 360. Now I could try subtracting 360 and getting another angle, but that would give me negative 660, and negative 660 is not within the domain that we're looking for. All right, let's see if we can get a coterminal angle with 300 degrees that would also be between negative 360 and 360. All right, adding 360 wouldn't be any good. It would give us 660. All right, too big. But subtracting 360 would be fine here. 300 minus 360 is negative 60 degrees. Now I could try subtracting 360 again, but negative 420 is outside of the domain that we're trying to find solutions for. All right, so using the unit circle, I was able to figure out that the solutions to this equation for our specified domain were these. We can say that x is equal, now I'm going to list these from least to greatest, you don't have to, but x is equal to negative 300 degrees, negative 60 degrees, positive 60 degrees, and positive 300 degrees. Okay, now if we hadn't limited our domain, we could have had an infinite number of solutions because we could have kept adding 360 or subtracting 360 here. Same there. Infinite number of solutions is not what we're looking for. There is a place for that, but that's not what IB is going to care for you to know. All right, so that's your first example of solving a trig equation using the unit circle. We've got 3 more that we're going to go through in this video, and I want to go ahead and get to the next one right now. All right, see, we're going to solve the equation 4 sine theta plus 5 is equal to 1. And this time, the domain that we're going to work with is negative 2 pi is less than or equal to theta is less than or equal to 2 pi. And what I want you to notice about that then is that the domain is given to us in radians, so our solutions are going to be in radians. All right, now let me go back to the previous slide really quickly to point out something that we're going to have to use for this one. Whenever you're solving a trig equation, one of the things that you're trying to do is to get a trig ratio by itself. Here we had the cosine of x by itself, and everything else was on the other side of the equation. Well, we're going to try to get the sine of theta by itself in this equation in order to find out the solutions that we want. And that's going to be a 2-step process. We're going to need to subtract the constant term here from both sides. Then we're going to have to divide by 4, which will give you this. Sine of theta is equal to negative 1. All right, and as soon as we have that trig ratio by itself, now we can start coming over to the unit circle and trying to find all the values in our domain that would make that equation true. All right, so where is the sine of an angle equal to negative 1? Or in other words, where is a y-coordinate negative 1? Well, hopefully you know that that's down here at 270 degrees. Or, since we're dealing with radians, we can say at 3 pi over 2, that's a place where the sine is equal to negative 1. All right, So now what we need to do is find any other angles that fit that same quality. We don't need to bother subtracting from pi here to find another angle with the same sine value, because there is no other position on a unit circle. Not here, not here, not here, not here. No other position on the unit circle where the sine is -1. But we do need to think about coterminal angles here. All right, so first let's try to make a coterminal angle by adding 2 pi. All right, so by going a positive 2 pi radians around the circle. Now if I add 2 pi, that means I would be adding 4 pi over 2, which would give us 7 pi over 2. Now 7 pi over 2 is coterminal with 3 pi over 2. But isn't that 3.5 pi? And 3.5 pi is not between -2 pi and +2 pi. So even though that's true, we're not going to use the 7 pi over 2. So let's see if we can find a smaller angle that's coterminal with 3 pi over 2 that does fit within the range of values that we're looking for. That means we're going to need to subtract 2 pi. And if we do that, we're going to get -pi over 2. And certainly -1/2 pi fits within the range of values that we're looking for. So I'm going to list that as one of my solutions right there. And then if we subtract 4 pi over 2 from that, we would get -5 pi over 2. Now that's -2.5 pi, and that doesn't fit within this range of values, does it? So we found out that there are 2 values that would make that equation true within our specified domain. Theta could either be equal to -pi over 2, or it could be equal to 3 pi over 2. All right, is this making sense to you yet? Hope so. We're working again with very simple trig equations, but I think you get the idea of how the unit circle is being used to aid in solving those equations. All right, 2 more to go. Let's try this next. All right, you see the equation that we're trying to solve. I want you to note that we are back into degrees here for our answers, and it's not from -360 to +360 anymore. It's from -180 to 540. So we'll see how that plays out in a little bit. And there's one other key thing that I want to point out to you right here. Notice that this equation doesn't just have a trig ratio, it has a trig ratio squared. You see the exponent right there for our tangent. So that's going to make a difference in how we solve this as well. Let's go ahead and begin by getting the trig ratio by itself, like we talked about in the previous example. So that's going to require us to subtract 1 from both sides. And so that gives us that the tangent squared of x is equal to 3. All right, now if you ever have an equation x squared equals 9 or m squared equals 25, you know that you take the square root of both sides in order to get the variable by itself. And same thing with trig ratios. If I have a trig ratio squared, then in order to figure out what the trig ratio is equal to, I simply take the square root of both sides. But also remember to take the positive and negative square root of both sides. So I can say that the tangent of x here would be equal to the plus or minus square root of 3. And what I'm going to do is I'm going to separate that into 2 different equations actually. Now this is going to happen often when you're solving trig equations where you've got basically a quadratic trig equation, meaning it was squared, and you're going to end up with 2 separate equations that you're trying to solve in the process of trying to solve that single quadratic trig equation. All right. What we need to do to find our solutions to the original equation is we need to find anything that makes either of these 2 equations true. So let's go to the unit circle. Trusting that you know the tangent values in the first quadrant, I think you know that the tangent of x equals the square root of 3 right there at 60 degrees. All right, and then of course you need to think about what's the other position that would have an equivalent tangent value to this angle right there. And you add 180 degrees to get that, so go to 240 degrees. Now that means the tangent of 240 degrees would also be the square root of 3. Now I'm going to try to color coordinate as much as I can in order to help you know what we're working with at each time here. Right now what I'm doing is I'm just looking at the solutions for this tangent of x equals the square root of 3. So let me highlight that in red because I'm writing at solutions on the unit circle in red. And both of these values that we found so far are indeed between -180 and 540. But we need all the values that are between -180 and 540 that have a tangent of square root of 3. Okay, so let's work with coterminal angles then. And let's see if adding 360 will get us values that fit within our domain. Well, adding 60 and 360 together gives you 420. That's less than 540, isn't it? So we can use that value. And if I add 360 to 240, well, that gives me 600, and 600 is a little bit too big, isn't it? So I'm not going to do that. Now let's also go back and subtract 360 degrees and get another set of coterminal angles. 60 minus 360 is negative 300. Well, isn't negative 300 less than negative 180? So we're not going to use that. I don't really need that comma there then. 240 minus 360 is negative 120, and negative 120 is within this range of values. So let me go ahead and list that as well as a solution. Now those four angles are the four angles where we have the tangent of x equal to the square root of 3 for this domain. We also need to find the angles where the tangent of x equals the negative square root of 3. Now I'm going to mark these in green, and I'll just color coordinate again there. Alright, now it turns out that whenever two angles have tangents that are opposites of one another, there's a couple ways you can think about where they are located in relation to one another. They're either reflections in the x-axis or they're reflections in the y-axis for one another. Let's go with the x-axis. 120 degrees, I meant reflection on the y-axis, 120 degrees would have a tangent that's equal to negative square root of 3. Then as always, you can add 180 to that to get something else that has the same tangent value. So 300 degrees would also have a tangent that's equal to negative square root of 3. And then let's go for coterminal angles for each of those. 120 plus 360 is 480. That fits within our range of values. Adding 360 to 480, that was going to give us something bigger than 540. If we add 360 to 300, that's going to give us something bigger than 540, so we don't have to worry about that. Let's go ahead and subtract. 120 minus 360 is negative 240. Negative 240 is too small for our range. And then 300 minus 360 is negative 60. Well, that'll work just fine. If I subtract 360 again, I'll get negative 420. Negative 420 would be too small. Alright, so it turned out that there are 8 solutions to the original equation right here, and they're the 8 that I've got listed on the unit circle right now. And I'm just going to list them out as my answer. You always want to write your answer, don't you, on a quiz or a test. So let's do that. Alright, now in this case, I've got a bunch of things that are opposites of one another. So I'm going to say, for instance, that theta can be equal to either positive or negative 60 degrees. It can be equal to either positive or negative, 120 degrees. And I think that's all the opposites. We also had nope, those were the only two negative angles, negative 60 and negative 120. But then we also had positive 240, positive 300 degrees, positive 420 degrees, and positive 480 degrees. Alright, hopefully you're feeling good about this. I'm going to have to give you a little bit of hint on the next equation, but then at the end, hopefully you'll be able to handle it on your own. Alright, last example. We're going to solve an equation using radians again, as you can see right here. And this equation is going to be different because I gave you two different trig ratios. It doesn't just have a sine or a cosine, it's got both of them. And I wanted to do that because there's a strategy, there are many, but there's a specific strategy that I want you to try whenever you've got two different trig ratios in the same equation. And that strategy is this. Anytime you have more than one trig ratio in an equation, the first thing you ought to consider doing is seeing, is there a way to reduce it to where you only have one trig ratio in the equation? Now, there's no way of canceling out the sine of theta or cosine of theta using addition or subtraction, but there is a way to use division here to get things to work out the way that we want them to. All right? I want to remind you of an identity that you've used before and you're going to start using a whole lot again, and that's that the tangent of theta is equal to the sine of theta divided by the cosine of theta. Alright, you know that. You might not know where I'm going with it so far. Well, I've got sine and I've got cosine in two separate terms right here. What I'm going to be able to do in order to make it so I've only got one trig ratio here is I'm going to be able to divide both terms here in this equation by cosine of theta. And the reason I chose cosine of theta is twofold. First of all, I knew that I would get a sine theta over cosine theta, and I can just make that into a tangent theta. Secondly, I knew I was going to have a cosine theta over cosine theta, and anything divided by itself is 1. So I'm down to just one trig ratio, right? I've now got the tangent of theta minus 1 is equal to 0. You should be able to solve that on your own from here. So pause the video if you think you can do that. Check it later. I'm going to continue right now though. Okay, so now we've got it down to a single trig ratio. Let's go ahead and get that trig ratio by itself. The tangent of theta equals 1. And let's think about where in the unit circle a tangent would be equal to 1. Tangent is equal to 1 anywhere sine and cosine are equal to one another. The first place that occurs is right there. Now we're dealing with radians, so that's pi over 4. And in the second place that would occur is half the circle away. Since we're dealing with radians, I want to add 1 pi to that. And if I'm adding 1 pi to pi over 4, I really want to add 4 pi over 4. And pi over 4 plus 4 pi over 4 is going to give you 5 pi over 4. Alright, so these are the two positions on a unit circle where we have angles whose tangent is equal to 1. Now, I do want you to notice that only one of these actually fits within our domain though, right? 5 pi over 4 is 1 1/4 pi, and that's bigger than pi, so that's a little too big. I'm going to put a little X through that. We're not actually going to be able to use it. Okay? We're also not going to be able to use anything bigger than 5 pi over 4, so there's no reason to add 2 pi to find any coterminal angles there. Alright? However, it does make sense to go ahead and subtract 2 pi. If I subtract 2 pi from 5 pi over 4, that's 5 pi over 4 minus 8 pi over 4. I get negative 3 pi over 4. Well, negative 3/4 pi is within our domain, isn't it? Let's subtract 2 pi again. That would give you negative 11 pi over 4. So that's negative, 2 3/4 pi. That still fits within our domain. If I subtract 2 pi again, I would get negative 19 pi over 4. And that's almost negative 5 pi, and negative 5 pi doesn't fit here. So we've gone too far. I'll cross that out. Alright, now let's see if we can find some angles that are coterminal with pi over 4 that also fit within our domain here. Now, adding 2 pi would give us something that's too big. Alright, that would give us 9 pi over 4, which would be, bigger than 1 pi. But let's subtract 2 pi. So pi over 4 minus 8 pi over 4, negative 7 pi over 4 will work. Okay, that's negative 1 3/4 pi. That will help us. And then let's subtract 2 pi again. That will give us negative 15 pi over 4. But that's closer to negative 4 pi, and that's outside of our domain here, so I'm going to cross that one out. Alright, turned out that the 4 answers that I didn't cross out are the ones that work for this equation in this domain. Alright, now I'm listing out the solutions. There's our 2 negative solutions. Actually, we had 3 negative solutions. I forgot the negative 7 pi over 4. And then we had 1 positive solution, which was positive pi over 4. Alright, you've gotten your introduction now to solving trigonometric equations using the unit circle. This is going to get a lot more in depth, but it really is pretty fun once you get the hang of it. Just got to pay attention to details, that's it. Thanks for your attention, everybody. I know it's a lot of hard work to pay attention for this long. Nevertheless, I do appreciate it. I will see you next time.